So for the analysis of earthquake analysis, that is mainly the dynamic load, we are mainly having different methods like equivalent static method and dynamic analysis method. In the equivalent static method, what we are doing is that we will be analyzing a system. If I am having a system like this, I can analyze the system. What we have been doing is that we will be assuming that the whole mass of the system is assumed to be at this floor, like let the mass be m1. If it is having another story, then also we will be taking it as this is m1, this is m2, like that. Then we will be analyzing it separately. We will be analyzing with the mass m1. We will be analyzing. We will be finding a time period t1. Then for m2 will be another time period. So if it is this is a 2 degree of freedom system, 2 degree of freedom systems, then it will be having 2 degrees of freedom. So the degrees of freedom in the system will be 2. Therefore, there will be 2 time periods t1 and t2. So for both the time periods, you will be getting omega 1 and omega 2, and we can find out what is the response mode shape, etc. So this method of analysis is that we are converting a system into two. This is a multi-degree of freedom system. But what we are doing is that we are converting it into 2 single degree of freedom systems separately, and we are finding out the time period, omega, the eigenvalues and all we are finding out. This is so far we have done. So that type of analysis is known as equivalent static method. But the responses from that method cannot be used directly due to the dynamic action. So we are mainly using dynamic analysis method. This method is normally we are doing it in using some softwares. Like for example, we will be using softwares like ETABS, or we can use, you have studied about STAD software, etc. We can perform this dynamic analysis. In the dynamic analysis, there are different methods are there. One is response spectrum method, model time history method, and time history method. These are the 3 methods that are depicted here in the our IS. The IS code is IS 1893. This is the IS code which you will be following, which we are mainly for the design. But as for your syllabus, you need to know a little bit about response spectrum method, how it is different from all the methods which we have studied. So that is the thing which we will be studying here. And this equivalent static method, or the method which we have studied now, will be used for regular structures with the time period less than 0.4 seconds. Regular structures means those structures are having, for example, the plan will be either rectangle or square, like that. And in irregular structures means the structure may be like this L-shaped structure, or it may be a T-shaped structure, like that. It can be like that. Or this is in the plan. The plan there will be irregularity. Or sometimes in the elevation. The elevation may be, this is a normal structure, the elevation. But sometimes some parts of the building may be at a lower part compared to the other part, like that. There maybe there is like this, a structure is there. So like these structures are there, these are irregular structures. In those structures, we will be following this type dynamic method of analysis. And in that, our discussion will be mainly on response spectrum method. So first you have to understand what is response spectrum. So response spectrums are the plots like this. I think you can see 3 plots are here. This is the plots which are representing response spectrum, and the first plot is of acceleration. The first plot is for acceleration versus the y-axis. The x-axis is time period. X-axis is time period. Next is velocity and versus time period. Third one, it is displacement, it versus time period. So response spectrum, we can say it as it is a graphical representation of how a structure will respond to a given seismic motion over a different range of frequencies. So it is of 3 types. Sometimes we can plot it with the acceleration, then it is called accelerator spectrum. When with velocity is called velocity spectrum, and if it is displacement, it is called displacement spectrum. And what it is done is that here we are plotting the maximum acceleration of a system against its natural frequency. Okay, the maximum acceleration against the natural frequency. So how this response? So response spectrum, it is a graphical representation that shows how a structure will respond. Respond means response is being measured in terms of acceleration. It is either in terms of displacement, or it can be in terms of velocity. Or in our words, how we can write? It can be in x term, x dot term, or x double dot, like that. Velocity, displacement, velocity, and acceleration. So 3 types of response spectrums are there. Now we have to know how this response spectrum is formulated. So these are some of the factors affecting response spectrum. One is earthquake magnitude. Larger earthquakes produce higher response spectrum. Then distance from the earthquake, that is from earthquake epicenter. Epicenter is the location at which the earthquake have generated. So if if we are taking a point near to the epicenter, it will be having a higher response spectrum. Then soil condition. Type of the soil at the site can significantly influence the amplification. So example, soft soils can amplify the ground motion. Then building character, that is the building height, the shape, the materials, that is another factor. Damping, the amount of energy dampation within a structure due to factors like friction, etc. So higher damping, it reduces the peak. Then size, then some other criteria like site specific condition, like local geological features, topography, fault activity can also influence the response spectrum. So the response spectrum, it is affected by, I have given the factors are 6 factors are given. What are the factors? Earthquake magnitude, distance from the earthquake epicenter, soil conditions, building characteristics, damping, and site specific conditions. So these are the, so here what we will be doing, how to develop a response spectrum. So let us look into that first, how we are getting this response spectrum. So before going into that, let us look into what is meant by time period. Time period means, so if I am having a structure as been shown here, so if I am having a structure, a single degree of freedom structure is there, I am just applying a force. Then then I am removing the force. Then what will happen to the structure? It will be oscillating like this. And it will oscillate and it will come to the natural position. That time taken, that is known as the time period. So the time period, it is given by the equation we have already studied. T is equal to 2 pi into root of m by k. 2 pi into root of m by k. So you can write T is equal to 2 pi into root of m by k. So time period is directly related to mass. So for example, if the mass is increasing, the time period will increase. So if a low mass, it will be having small time period. High mass, it is having large time period. That is directly it is related. Then similar to stiffness. If the stiffness is higher, time period will be less. That is the thing. Now, that is the thing. Time period is higher, then if the stiffness is higher, time period will be less. It is in the opposite way. Now, so if I am having a mass like this, you can see the figure, I am applying, an earthquake force is being applied here. Okay, an earthquake force. Then what will happen to the structure? It will have a displacement. It will be displacing like this. Sometimes it may be like this, or sometimes the displacement will be very large. It will be displacing. So I will be plotting the displacement with respect to time. So here you can see I am plotting the displacement with respect to time. So here the maximum displacement is happening here at this point. For example, I am plotting acceleration. If I know the displacement, I can easily find out the acceleration. Then this is the largest acceleration. So you can see if I am having the acceleration, then This largest acceleration is known as maximum magnitude. This is the maximum or maximum magnitude is known as absolute acceleration. So response spectrum means, for example, here I am trying to draw how to get the response spectrum. So response spectrum is a plot of maximum acceleration with respect to time period. So first of all, I am considering a frame which is having a length. Let the length be L1. Then the time period which I got it is 0.02. How I am getting the time period? I am getting the time period in such a that time period means it is the where I will be getting the maximum acceleration. So here in this point I am getting the maximum acceleration. So I will be getting a time period. I will be plotting that. Let this be the acceleration. So at this time period, so in this, for this system, for this condition, when the length is L1 or the height is L1, I have got the maximum magnitude. I am marking it as this point. So this is at a time, let the time period be 0.2 seconds. So at 0.2 seconds, I am marking this one. So that is the, for this system, for this building, the maximum time period is 0.2. The natural time period is 0.2. Now I am in the same system. What I am changing is I am maintaining the mass is same. Mass is same. Damping is also same. I am only increasing the height. Let the height be L2 or H2. Then I am getting another time period. Then corresponding to that, I am finding the maximum acceleration. So I am plotting another. Let this time period be 1.2. Okay, I am just taking example. So the first one was 0.2. Now it is 1.2 like that. So what I do is that I will be changing the height. So as the height increases, what will change? The time period will change. The natural time period will change. For a particular building with the same mass and damping, we are just increasing the height. So as the height increases, the time period will be changing. So at each natural time period, we will be getting some maximum acceleration. So I will be getting lot of curves. That is, for example, if I am drawing like this, for time period 0.2 seconds, I will be getting a acceleration curve like this. Then at 0.4 seconds, I will be getting another maximum like that. I will be getting lot of points corresponding to the maximum, corresponding to the time period. So here in this building we have not changed the mass. We have not changed the damping. We have only changed the height. So that what has happened? The time period is changing. So as the time period is, natural time period is changing, I will be getting different maximum accelerations. So I am just plotting this like this. I will be getting lot of points. Okay, lot of points I will be getting, maybe like this, different points I will be getting, and I will be connecting all these points. So this represents the response spectrum, acceleration response spectrum. If it is velocity, it is velocity response. So what is response spectrum? Response spectrum, it is the plot of maximum, that is response spectrum is of three types. It can be acceleration response spectrum, velocity response spectrum, and a displacement response spectrum. So if it is acceleration response spectrum, it means it is a plot of maximum accelerations that has happened in a. So here we will be considering only a single degree of freedom. The multi-degree of freedom will not be considered. So at each single degree of freedom system, I am finding I am changing the length, and I am making all other mass, damping, etc. are same. Then I will be getting a plot. Such a plot is known as acceleration response spectrum. So here you can see. So for example, at time period 0.9, we have got some maximum acceleration. So this is how we will be getting. Now, so I will be getting so this is corresponding to, so the first graph, this is corresponding to a single earthquake. Single earthquake means an earthquake of same magnitude. So how a magnitude of it is mainly in Richter scale. For example, 1 Richter scale or 2 Richter scale, like that. Then, so I will be getting first graph. This is my first graph. Second one, then for each earthquake, we will look on that. So first earthquake, so I'm drawing the accelerogram. So this is the variation of in respect to E1, first earthquake. Now, to the same building, I am applying an earthquake of different magnitude. So, its response may be like this. It will be having a different response. Then that may be E2. Like that, we will be plotting for different types of earthquake. Let's this one be for E1 earthquake. Next one for E2 earthquake. Like E1, E2 means E1 will be of one Richter scale. E2 will be of another magnitude. The magnitude will be changing. So, we will be getting a graph like this. Okay. And we are plotting a mean graph with the help of all the values we have obtained. So, a graph you will be getting like this. You can see a darker line here. This represents, this is the envelope response spectrum. And also it is known as design response spectrum. So, what we have done, we have plotted, we have first created lot of response spectrums corresponding to a single earthquake, E1 earthquake. Then, we to the same building, we have applied earthquake, another earthquake, let it be E2 of another magnitude. Like that, we will be plotting lot of earthquakes, lot of responses, and we will be getting a mean graph. This graph is known as design response spectrum. So, first is response spectrum. That is a plot showing a single earthquake. Design response spectrum, it is the envelope or the mean graph showing the mean plot showing the response spectrum of lot of earthquakes. So, and the acceleration. So, if I am having, for example, I am taking, this is the first time period, 1.5 I am taking. This here you can see this is acceleration here. That acceleration is known as, another word it is there, it is known as spectral acceleration. Earlier time we used acceleration, it was an acceleration of a single term. Spectral acceleration means it is an acceleration which we are getting from a design response spectrum. Okay, that is meant by spectral acceleration, SA. Okay, now this is meant by response spectrum. Now, why we have found out these response spectrums and everything, why we are using it? The reason is that, so our main aim in earthquake or dynamic analysis is that I need to find out the force that is acting in a building. Okay, because we cannot calculate the earthquake. Earthquake is just a motion. Earthquake is just a horizontal motion, and we are in dynamic analysis. Our aim is mainly to find out the lateral force. For that only we are using all the equations. So, the lateral force is equal to VB. It is given in the 7.2 clause of IS 1893. VB is equal to AH into W, where W it is the seismic weight. W is the seismic weight. Weight means it consists of dead load plus live load. So, there is some relations are there. That is, if the dead load we will be taking as 100%, but live load we will be sometimes taking as 25% or 50%. For example, if the live load is less than 3 kilonewton per meter square, we will be taking 25% or 0.25, 25%. If the live load is greater than 3 kilonewton per meter square, we will be taking 50%. So, W will be dead load plus some percentage of live load. For example, 25% of live load. So, we can calculate what is W. What is dead load? Dead load means the if I am having a beam of size, for example, a beam of size 23 by 50 meters, 50 mm or 50 centimeters, sorry, 23 centimeter. So, the dead load will be 23 into 50 into the length, for example, 4 meter beam into density of concrete is 25 kilonewton per meter cube. So, I can find out the dead load. Okay. Then, live load we can find out using, we are having the code IS 875 part 2. So, some buildings we will be giving as 3 kilonewton, some rooms we will be giving as 2 kilonewton. It depends upon the room. Okay, for example, for a residential room, we will be giving the live load as 2 kilonewton per meter square. But for a college classroom, we will be giving, as a number of students are more, we may be giving it as 4 kilonewton per meter square. It all depends on the type of the room. I am not going to that details and all. So what has happened is that this is how we will be finding the W. So our main aim is to find out this lateral force. So W, lateral force depends upon AH into W. Now what is this AH? So that is the thing which we have to know. AH, it is the design horizontal seismic coefficient. Design horizontal seismic coefficient. It is equal to Z by 2 into SA by G into R by I. This SA, it is the spectral acceleration. So that we have to find out from the response spectrum. Now Z, it is the seismic zone factor. I, here I, it is the importance factor. Importance factor means based on the building. For example, for a critical and lifeline structures, for example hospitals, thermal power plants, etc., we will be taking it as 1.5. For other buildings like hostels or some assembly halls, etc., we will be going for 1.2. And I, it is the and 1 for other buildings, residential building and all. Then R stands for response reduction factor. Response reduction factor. Okay, that and all we will be that is not needed as per your syllabus and all. Just for I am just trying to give you an idea about why we are finding out this SA. SA is the spectral acceleration. So here, so in the IS code itself, this is the curve. So if I have to find out the spectral acceleration, you can see here this is SA by G. Normally we will be representing in terms of gravity. That is why it is SA by G. Now time period is written 0, 1, 2, 3 seconds. Now here this spectral acceleration depends upon some factors we have followed. Depends upon the soil type. So if it is rocky soil, we will be going for the first curve. If it is medium soil, we will be going for the second curve, like that. So based on the soil and everything, we can find out, and just to find out if I am having the response spectrum directly, I can find out what is the time period. If I know the time period, I can directly find out SA by G, and I can directly find out the AH. From the AH, I can find out the lateral force. Once I got the lateral force, I can just put it in the, for example, I think you have studied about lateral frames. If a horizontal force is acting here, I think you know how to analyze the frame, either by moment distribution method or Canny's method, etc. We can easily find out what is the moment. So I can design for the moment like that. So that is why we are using this response spectrum. So the thing is that when I am for most of the time, we will not be able to get, if I am planning a building in Trivandrum, I can use response spectrum only if I have a response spectrum plot of Trivandrum. Otherwise, what I have to do, I have to model. I will be creating lot of models, and I will be giving some random values, and I will be finding out a response spectrum. I have to plot it. From the response spectrum, I can find out the value of AH, and I can then find out the value of lateral force. Like that. That is how it is been done in reality. Okay. So here we have discussed up to here. So response spectrum. So you can see here how we can obtain the response spectrum. That is, if I need to know the location. For example, our location is Trivandrum. Then soil type, I am taking it as medium soil. So then some using our IS code is IS 1893. From this code, I can find out, if I am having the time period, I can easily find out spectral acceleration SA. So this is how I can find out the spectral acceleration. Now let us look into a problem, how to find out the response spectrum of a single degree of freedom system. Okay. In your syllabus, it is second thing it is multi-degree. So today we will discuss on how to find out the response spectrum of a response spectrum method for a single degree. If you know the single degree of freedom, it is same way only we will be doing the multi-degree of freedom. So let us first into a single degree. So here you can see a plan of a building, and here you can see a single degree freedom building is there. Now this response modification factor, it is based on the building only. Sometimes it is 3 or sometimes it is taken as 5. We will discuss on that just to in your mind. The total weight, I can easily find out what is the weight of the building. So I will be getting the mass and all. Now the time period, by some analysis I can find out the time period. So I think you know what is the time period is equal to 2 pi into root of m by k. So if I am having mass, if I am having k, I can easily find out the time period. So let the time period be here. I am giving an example only, 0.65 seconds. Now I have got the time period, for 0.65 seconds, I can find out what is the value, SA. So I will be getting SA by G is equal to 0.124, that much. So if I know what is the value of acceleration, then I can find out the force is equal to, this is another equation, sample equation only I have written. Our equation is force is equal to AH into W. So you have to find out AH. After finding out the AH, I can find out the value of W, and from that I can find out the seismic force. For example, in the x direction I have found out the seismic force as 75 kilonewton. So here in this problem I have used a different equation only, but you can, for the exam point of view, you can just numerical problems will not be asked from here. Okay, so just to know the steps only. Now in the y direction, similarly in the y direction I will be getting some force. Okay, y direction I am getting a force of 119 kilonewton. So in the x direction I am getting 79, y direction I am getting 119. So in this the seismic force we will be getting the in Fx, we will be taking it as, so here one thing you need to keep in mind is that for every buildings we will be analyzing it in two methods. One method is equivalent static method, other is response spectrum method. So what we do is that we will be finding out the forces in equivalent static method also. That is, we will be finding out Fx and Fy. So for example, one Fx is 100 and Fy I have got at 200. Then using Rx I am finding out the Fx as response spectrum I am finding out. For example, this is taken as 50 and this one is taken as, I will be for example I am getting it as 215. Okay, so you can just, so here if I am getting this difference, here you can see, here it is only a difference of 15 kilonewton, but here there is a difference of 50 kilonewton. So normally what we will doing is that we have to change the value of the, we have to, this is not a correct value. The minimum 85%, the equivalent, the response spectrum load should be minimum 85% of equivalent static load. So what is 85% of 100? It is 85 kilonewton. 85 kilonewton. Or no, or in normally in the safety point of view, what we do is that we will be making the response spectrum force also the same. That is, this 50 we will be changing it to 100. Okay. So this is done only when we are getting a value of the force less than 85% of the equivalent static method. Okay, so this is how we will be doing the response spectrum analysis of a single degree of freedom. So what we have done, first of all we have to find out the location, then we will be finding out the soil type. That things we can directly get from the data, from the plan itself. We will be able to understand, or from the soil report we will be getting what is the soil type, and the location we can get it from the site plan. Then using the IS codes we have to find out the time period and the acceleration. Now then we will be finding out by using two methods, equivalent static method and response method. These two methods we will be using simultaneously. By both the methods we will be finding out the forces, and the forces should be almost the same, and if it is less than 85%, what we do is that we have to change the response spectrum force to the other one. Sometimes another thing is there, here it is 50 I have written. Sometimes this can be 150. It can give a higher value. That also it is not acceptable. So it should not be too small or too large. If it is 150, we have to reduce it. So that is a way in which we will be doing the response spectrum analysis. So normally in all the in our design which we are doing now, we are following response spectrum. So as per your point of view, you need to know what is a response spectrum, Then what are the types of response spectrum, factors affecting the response spectrum. Then these are the applications, that is, it is mainly used for structural design, seismic hazard assessment, for the code development and performance evaluation. These are the applications of the response spectrum. Then some idea about how we are doing this. So this is how how the response spectrum and how to find out the value of the forces using response spectrum for a single degree of freedom. Now let us focus on, as per your syllabus, you need to understand about response spectrum of multi-story building, that is MDOF buildings also. Multi-degree of freedom systems also we need to find out. So I think multi-degree of freedom system we will take up in the next class. Okay.